So up till now, we've been talking about how we read and write data from a database. A transaction would be considered a collection of steps where you're doing reads and writes from a database. For example, we could have, as an example, you want to transfer, let's say, $100 from your savings account to put it into your checking account. Maybe you've written a check and you want to make sure the check doesn't bounce. So you go over to the ATM and you do a transaction. You transfer money from one account to another. So the account, the entire account, could be a series of reads and writes to a database. So for example, we could read your checking balance, then we take your checking balance and we subtract 100 from it. And then we write your checking balance back to the database. These reads and writes, of course, would be turned into, these are like stored procedures for SQL statements. Okay, and then we would read your checking balance, add 100 to it, and then write that balance back to the database. So what I have here down in the notes is that the reads and the writes are actually transactions into the database. And these computations, the minus 100 and plus 100, those are done, local variables are doing that, and then taking the results and speaking back to the database. So the question is, what if you were to do a transaction like this? Well, you'd want one of two things to happen, is either for the entire transaction to have not happened, or for the entire transaction to have happened. You don't want the step where you lose $100, gets successfully done, but it doesn't show up in your checking account, then you would actually have lost $100. So a transaction, we need to have the concept of kind of an all or nothing situation. So we want the transaction to have this so-called acid properties, which are autonomicity, consistency, isolation, and durability. And an operation is considered atomic if either the entire operation is done and reflected properly in the database, or none of the operation is done. We don't want parts of your transaction to be done and other parts to not be done. So a transaction is a sequence of reads and writes to a database that should be done either all or nothing. Consistency is if the execution of a transaction was done in isolation, meaning not done along with other transactions that are going on in the database at the same time, the results would be the same. And I'll go over an example of that shortly. Isolation is, even though multiple transactions may execute concurrently, the system is going to guarantee that for any pair of transactions, let's say transaction I and transaction J, it appears that transaction I or J either finished executing, J finished before I, or I finished before J. And again, the example I'm going to go over shortly will cover that. And then durability would be any time changes are made to the database. You know, if the transfer of money, for example, was completed, then we would never have to worry that it would be lost as data in the database. So, for example, in a transaction like this, where we're transferring money, we would want for the autonomicity part of that transaction, we would either want the transfer of the funds to be recorded in the data or not. For consistency, we would like the sum of the checking accounts and the sum of the savings accounts to be the same. So no matter what happens, if the money is transferred, the customer should not be losing money at all. Isolation, there must be no effect on the transactions that were running concurrently. Other transactions that were happening, possibly even affecting your checking and savings account, should not be affected by the fact that this transaction ran. And then as far as durability is concerned, is once the customer is notified the successful completion of the transaction, that the money was there, there would never be any way to have it undone. Okay. So an example would be if we had a transaction like this, if we had a transaction like this, for example, suppose you had $1,000 in your savings account and $0 in your checking account. And suppose we had two transactions going on at the same time. The first transaction is you're transferring $100 from savings to checking. And the second transaction is that the bank is coming by and giving every account 5% interest, even though that's a very high interest rate, kind of makes the math easy. So that's a separate transaction that's coming and gonna hit the same two accounts at the same time. So, for example, if transaction 1 happened first and transaction 2 happened second, if first, $100 was transferred from checking to savings, and then both accounts were given 5% interest, the savings account would have $900, the checking account would have $100 after the first transaction was done. Then they both get 5% interest, and the savings account would go to $945 and the checking would go to $105. So the customer would have a total of $1,050. If the second transaction happened first, and what's going to determine which one comes first? It's actually luck, right? Because you're going to go to the ATM, put your card in, you're going to transfer money from one account to the other. The bank maybe comes by at 3 o'clock in the morning and gives everyone interest. So if you happen to do the transfer right before the interest came through or right after, would determine which of the two transactions happened in which order. So either order would be considered consistent. So if the schedule came out that transaction 2 was done first, the interest was given first, and then the transfer of money from savings to checking was done second, then the 5% interest would have been given to the savings account, giving the savings account $1,050. And then after that, $100 would be transferred over to checking. So then we would have $950 and $100 as opposed to $945 and $105. In either case, the customer has $1,050, and if the customer logged in and saw that two transactions happened, one the transfer and number 2 the interest was paid, they would look at either one of these two results and say, yeah, that's consistent. Even though they're two different results, the customer would say, okay, yeah, no problem. So an issue could come if we had this situation. Suppose the first transaction was running and it updated the savings account. In other words, it subtracted $100 from the savings account. And then the system said, okay, hold on, something else is going on at the moment. We don't want to have this transaction hog up the whole system, so we'll let another transaction run for a little while. And this is the one where the checking and the savings balances were given 5% interest. So then the balances were read, 5% was added to it, and then the balances were written back. And then we came back to this transaction and finished up where we left off. And then we said, oh, okay, let's add $100 to the checking account. So in this case, the $100 that was temporarily missing from this customer's accounts, it didn't appear in the checking or savings. It was subtracted from the checking but hadn't been added to the savings. When the bank's interest came along, that $100 didn't get its interest. So this person would have $945 in savings and only $100 in checking. So the total would be $1,045, and they'd be actually missing $5. This result is considered inconsistent with what the intentions of this transaction and this transaction are. The transactions could be done in either order, and we would find these two account balances consistent with the intention of the transactions, as long as they were done in one order or the other. But the fact that they were done in this particular order, where we did part 1 of this transaction, then this one ran, and then we came back and finished part 2, we ended up having inconsistent results. Okay, so this leads to the topic of a schedule. So the schedule in that case would be, we could have a schedule of transaction 1 and followed by transaction 2, or transaction 2 followed by transaction 1. So a particular schedule for a series of transactions. The schedule is a set of transactions, is the order in which the transactions are done, and on a particular day on a multiprocessing system. A recoverable schedule is one where for each pair of transactions, transaction I and transaction J, such that J reads data that was previously written by transaction I, then what that means is it has to appear as though J finishes after I. So the commit, which is the step where a transaction says, I've done all my processing and my data is consistent, I'm ready to now say this transaction is officially over. So the commit of operation of transaction I has to appear before J. J cannot finish unless I claims it is officially finished. If I declares it can't be finished because, for an example, something like this happened, if this is transaction I and this is transaction J, and then I says I can't be finished, and some other transaction is depending on this thing finishing, otherwise it's no good, then that other transaction would also fail. So that would be a recoverable schedule. Schedule is one where every pair of if a transaction J reads a value that was set by I, then it has to be as if on that day the transaction I went first and transaction J went second, because J is taking that value and creating new data and probably writing that data to the database. Okay. A cascadeless schedule is even if the schedules are recoverable, to recover correctly from a failure of transactions, we may have to roll back several transactions. So for example, if 3 needs 2 to finish before 3 can be considered finished, and 2 needs 1 to finish before 2 can be considered finished, then transaction 3 must roll back. If transaction 1 then fails, 3 must roll back, and then 2 must roll back, and then 1 needs to be rolled back. Rolled back is where you take the data and rewrite the data the way it was before your transaction ever started, so you could then start over again. Okay. So cascading rollbacks are undesirable since it leads to undoing a significant amount of work. And the goal is to have the schedules be cascadeless. Okay. So the commit and rollback. So our data manipulation language, our SQL, must include constructs for these type of transactions. So we could have a commit work, which commits the current transactions and begins a new one. So in other words, if our transaction hits a point where we're reading some fields, making some computations, writing fields back, and we get to a point where we say we are done, we believe everything we've done is consistent, we put in a commit, the database management system will say, are all the transactions before us that we require they commit successfully before we can declare ourselves successful, have they finished? And once they finish, then our commit will be processed. The rollback, putting that in our transaction will cause our transaction to abort. Okay, so serializability or a precedence graph would mean as transactions are being entered into our system, we're looking at are our transactions reading from fields that a previous transaction has written. That would mean we would have to finish, we can only finish if the transaction that we read data that they produce can finish in a schedule before us. So they would have to be able to commit, otherwise we can't commit. So what we can do is every time a transaction enters the database system, we can add a node to a graph. And then anytime there is let's say for example, we have a transaction 1, transaction 2, and transaction 3. If transaction 1 reads data that was produced by transaction 2, then transaction 2 must complete before transaction 1 can complete. And if transaction 3 reads some data that was produced by transaction 2, then the only way transaction 3 can be considered successfully completing would be if transaction 1 can complete. So, in this particular graph, we're basically saying that transaction 1 must complete before transaction 2 can complete, and transaction 2 must complete before transaction 1 can complete. So these two are going to have a problem, and then transaction 3 requires that transaction 1 and transaction 2 must complete first. So we could have a situation where this could be the transfer of, well, we could have, this is the transfer of money from checking to savings, and then this is the interest. But because one transaction wrote to a field that this one then read and tried to read, this would have to finish after this one finishes. Then this one read and wrote a field, the checking, the money was writing to, the checking balance, which would make the transaction that was writing to, the transaction that was reading the value that would, this transaction was reading the value this one wrote. So each one of these has to finish after the other one. And we'd have a problem. So we'd have to say, okay, so, wait, let me just go back. If we had this situation, transaction 1 reads a field and writes a field. Transaction 2 then reads a field that was written by this transaction. That means at the end of the day, the only way we can consider these transactions consistent would be as if it ran like this transaction ran first, and then this transaction in its entirety ran second. But the fact that this transaction wrote the checking balance, which this one then later on read, then this transaction must finish in a schedule where it's after this one. So that could put us in a situation like this. The transfer transaction has to finish before the interest transaction can finish, but the interest transaction has to wait for the transaction, the transfer transaction to finish. So both of these transactions would have to be rolled back. In other words, we have to say, let's put the database back to the way it was before either one started. We'll take like a timeout, and then we will say that we'll start the transactions over and we'll do them sequentially. And then in this case also, 3 must have read a field that 1 produced, and 3 also read a field that 2 produced. So now 3 cannot be considered legitimately finished until 1 and 2 have both finished. So what we're doing is every time a transaction enters the system, we're maintaining this graph, and we're adding a node for the transaction, and then any time it reads a field that another transaction had created, we add an arrow to that graph. And then we have to go looking for cycles in the graph. The only way all the transactions can finish is if there is a path from one to the other one with no cycles. And then we could say, okay, let these transactions continue running on a time-sharing system, but as long as there's a path from one through the last one without any cycles, the data will be as consistent as if the transactions ran in that sequential order. So then we'd be okay, as long as there's no cycles in this graph. So the states of a transaction could be the transaction is active, which is the initial state, which says it is currently running. Partially committed, which would be after the transactions statements have been executed, but we're issuing a commitment. We want to say that we're done, and we're checking, the database is checking the graphs to see if everything that needed to be committed before us has finished, then we could be officially considered finished. We can go into a state of failed, which is after the discovery of normal execution, there's we cannot continue. So if for any reason we're trying to write to a field we don't have access to, or the power goes out or something like that, we're failed. We could be considered in the aborted state if after the transaction has been rolled back from the database, and then the database has been restored to its data prior to our transaction starting, we have officially been aborted, and then we could start over again. And committed means we made updates to the database as if what our transaction was trying to do. For example, if it was trying to take money from checking and move it to savings, we did all those steps. We told the database we're done by issuing a commit, and then the database had to check that every transaction that needed to complete before us had committed and successfully finished before they could declare us finished. So those are the states of a transaction, and then the state transaction diagram looks something like this. You can bounce around from state to state as events are happening. I'm sorry? Okay. Okay. So now the active, you can go from the active state to partially committed to finally committed. You can go from active to being in a failed state, which would then get you to the aborted state. It's possible you could just leave the system and say that transaction didn't happen. Or the transaction could then start over once the database has been rolled back to its data prior to you, prior to your transaction, which ended up getting aborted, started. One of the tricks that we could do, but this could take up a lot of space, is to have a shadow copy of the database. So we take a copy of the database, all the fields, the checking and savings account, or whatever fields you're about to touch, before you start doing anything. Then let your transaction run. If your transaction fails for any reason, then we could simply just write all the variables, the ones that you read and wrote from, write them back to the values they were before you started. That's called the shadow copy. Okay, we could use a lock-based protocol, and this topic does come up in the operating systems class too. But the idea is that one way to ensure serializability is to require that the data items can be accessed, have mutual exclusion. So a lock is requested from the operating system. We can have shared locks or exclusive locks. And the idea of the way that locking ends up working, so for example, you can lock out the fields of the checking account and the savings account so that no other process can use them. And the idea basically goes like this. This would be our transaction. This would be our transaction where we would go, we would lock out the savings account, read the savings account, update the savings account, write the savings account, unlock the savings account. Then we would, so this transaction doesn't really even know about this one. This is just the way the schedule happened to lay out that on a particular day. But the idea is that if we locked it and then unlocked it, then the next transaction comes in, it locks the savings account, reads it, updates it, writes it, unlocks it. The idea was that if we ran out of time, say halfway through doing this transaction and this one started, when it goes to run the lock method or function against the database, if it has not been unlocked, then this transaction will get stuck right at this point. It will not be able to proceed until some other transaction unlocked it, and then it would be able to proceed. So the idea that this would happen, where we were updating these fields and then these ones changed, would not be the case. So we could put locks around the savings and the checking balances. Now, the way this code is written, we still have the problem where we could lose money in the database. It would have been better, since if we would have considered having one lock for both the checking and the savings account. Lock them both out, make the changes that you need to make so you don't have this situation where you lose the money from the savings account, then the interest comes through and then you put the money back. So, or another thing we could do is we could have gotten the lock for the savings account and the checking account up here at the beginning, which then when these went to ask for the savings account lock, they wouldn't have gotten it. And so we could do that concept too. So there's a couple ways we could handle the locking, but just because, what I'm showing in this case, just because the operating system gives you a locking mechanism, does not mean you're guaranteed that your transactions will produce consistent data. You still have to use the locks correctly. And the locks are generally run through a lock manager part of the database, so it's usually done through a hash table, because we want to do lookups very quickly on whether an element is locked or not. So we have a hash table, it gives us a hash value, and we check what that hash table array is pointing to. If there are locks that have a collision in the hash table, we could have a linked list of locks for a transaction. So we could have a transaction, you look it up in a hash table, and then it has a list, below it has a list of all the locks that it currently holds. So you might remember from your operating systems classes, we could have a deadlock situation in a database. There are four, again, I'm not going to cover this, you can look in an operating systems textbook, but there are four conditions of there being the possibility of a deadlock in your system. And once you introduce locks, a transaction could grab a lock, could grab permission, exclusive access to one resource, and then ask for a second one, and another transaction has that second lock and is asking for the first one. And now both of those transactions are waiting for each other to finish, so they'll never get finished. Techniques of deadlock avoidance would be to look at the four necessary conditions of deadlocks, a system that allows the possibility of a deadlock, and then picking one of those four and saying my system should never have that. And what databases sometimes do is focus on this last one, this idea of chaining, so getting the locks in a particular order. So the idea of, which is sometimes unrealistic in the database world, is somewhat realistic in the, a method of deadlock avoidance, which is somewhat unrealistic in the operating systems world, is somewhat realistic in the database world. And that is the idea that you would gather all your locks at the very beginning. Or you would, well, first of all, a loose version of it is you gather your locks in two phases. So your transaction has a section where you're gathering locks. You may also be doing data transactions. And then you hit a certain point where when you start releasing locks, you never ask for any more locks. So at the beginning of your transaction, you're gathering up locks, doing steps along the way, and then once you start releasing locks, you just release them all. So if you ever get to the point where you're stuck, you're guaranteed that what you're stuck waiting for will be coming at some point. Some other transaction, when it hits its freeing up stage, will release the locks. There's a version of the strict two-phase locking. That's where the very first set of steps in your transaction is gather all the locks you'll ever need. And then the final steps are release all the locks you have. And then between the two, you're doing your transactions. And then the idea is that as you're gathering up all the locks, if you ever get stuck, if you ever get turned into a deadlock situation, then you haven't done any transactions against the database, so if your transaction gets aborted, you just free up all your locks and start over again. So it'll guarantee that you won't have to undo any transactions to the database. Another protocol for doing this is the timestamp ordering protocol. So transactions enter a system, they get timestamped when they enter the system. We also are going to keep track of when a write is done, and a write is done to a particular data field, not just any write. So we'd have a write timestamp for Q, the largest timestamp of any transaction executed that does a write of variable Q successfully. And also for reads. So the idea, so the idea in this protocol is that, let's say for example, we have a transaction that, we have a transaction A. So time is going this way. So transaction A starts at this point in time. And then at this point in time, transaction reads, that's an R, reads variable X. Then it does some kind of processing, and then all of a sudden it writes to the database, it writes the value of variable X. Then it keeps going along, and maybe during this period of time it is taken off the processor and some other transaction is running. Then maybe this one's taken off the processor, and then this one starts running, and then this is taken off the processor, and this one runs, and then this one runs, and so on. So they're time sharing the same processor, and they're also reading and writing from the same data fields. So at this point in time, right here, is where transaction B begins. So transaction B begins right here. So B begins after transaction A wrote the variable for X. Then transaction B comes in, I guess without reading X, it just writes X. It says, I have a new value for, I'm sorry, no, this is variable Y. So it writes a variable Y, and then it does some more processing, but all we're doing is keeping track of what it does with the database. But it does some more processing and apparently doesn't write anything at the end of its transaction. At this point in time, transaction C comes along, and C starts at this point. C reads the variable X, does some type of computation, and then writes the variable X, and keeps running for a little bit more time. A is running, B is running, C is running, A, B, C, maybe they're time sharing. And then eventually C is not finished yet, but it says, I think I've done everything I need to do. So it would issue a commit. It would issue the commit, we call the commit function, saying, I'm done with everything. Please, notify me that everything's okay, and I could actually tell my customer, yes, your database transaction has been completed. B and A continue running in parallel with each other, and then A reads a value Y, which was written by transaction B. So B reads Y, and then does some kind of computation with Y, and then writes a new value for Y. But at this point, B finishes and says to the database, I would like to commit my results, and it wrote something to the database. So if it writes something to a database, it wants to know that my write was been taken by the database, it's not going to be backed out, and I'm not going to have to start over again. So it issues a commit here. And then when this transaction A finally finishes, A says, may I finish? I want to do a commit, and I want to know from the database, is my process completed? So here, transaction C is partially committed. So transaction C got to this point and says, I think I'm done. Let me know if you see any problems. Asking the database, let me know if there are any problems. But it needs to wait for A to finish before it can be committed. The reason it needs to wait for A to finish is it read the value X, which was written previously by transaction A. So at the end of the day, it has to be, even though these transactions are being interwoven, this one runs for a little while, then this runs, then this runs, it's going to have the effect of A ran first, start to finish, and then later C ran, because C is going to run as if it took the update that A did. So it has to be as though A ran first and in its entirety, and then C ran first in its entirety after A finished. Whatever those database results are would be consistent with one particular schedule. So C can only be considered legitimate if A actually finishes. If A doesn't finish, then C ran with data created by A, which then was undone, which would then make C's transaction invalid. So C is partially committed because at this point it says it wants to finish, but it can't finish because A needs to finish. A fails because B performed a write of the variable Y, and A later did a read of X. So this transaction wrote a variable that this one read. So A later did a read of Y, but A started before B. So therefore, since A started before B, then if this transaction wrote a variable and then this one ran second, then it would be as if B ran before A, and A needed to run, as we said, before C. So because transaction B started after A started, but it wrote a variable that A later read, then A and B have to be undone, have to be rolled back and start over. So therefore, A must be rolled back, which causes C to be rolled back. Because A is going to be rolled back. B can go on to finish because B was really undisturbed by this. So in this case, just a quick little recap of what's going on in this case. Is transaction A started first, read the value of X, wrote the value of X. Then transaction B started. B wrote Y, so B is fine, it's independent of everything that's going on so far. Then transaction C started. C, reading the value of X, it's the value set by transaction A at this point. So if transaction A can go on and finish, that's fine. Then our database will reflect the content as if transaction A ran first, transaction C ran second. As long as A completes, C can then complete. So C writes its value back. But we are using the timestamp ordering protocol, which basically says if this transaction starts after this one started, if this wrote a variable that this later read, then this transaction has to be backed out of our system. So since A has to be backed out of our system, we have to go back to the value of X before A ever started, but C has already picked up the modified version that we're now taking out of the database so we can start transaction A over again. So that A being rolled back causes C to be rolled back, but B was not rolled back. So what this transaction timestamp protocol does is instead of in the locking phase where you tell every transaction, make sure you can run start to finish before you start. And then B says, make sure you can run start to finish before you start. And then C says, make sure you can run start to finish before you can start. Well, C would get stuck at the very beginning and would have to wait until A finished before C can even get started. So by doing this timestamp thing, we're hoping the benefit is, we're going to let these transactions run. We hope that this scenario where transactions need to be rolled back, we hope it doesn't happen that often, but if it does happen that often, then our system has to take a timeout, change the database back to the way it was before all the transactions started. We could do that using a shadow copy of the database. And then what we can do is start transaction A or C over again. We would take a timeout, we would run A start to finish, and then we'd run C start to finish. And then let the system go back to multi-processing again. So yeah, so that's the story on that. And then I know you guys have been pretty quiet, but if there's any questions.